완전히 결정론적으로 뭔가가 결정되는 답이 구해지는 이런 교육을 받다 보니까 항상 우리는 그런 식에 익숙해져 있어요. 스페어 개수 몇 개야? 3개. 이걸 좋아하지 3개일까? 4개일까? 이거는 되게 싫어요, 사람들이. 근데 다행히 스페어야 그렇게 우리가 수학적으로 계산할 수 있대지만 다른 지표들은 그렇게 계산할 수 있다 없다? 없는 게 훨씬 많아요, 사실. 아까 얘기했던 리스크 오브 쇼티지 뭐예요? 확률로 계산하네. 확률 뭐 이제 퍼센티지. 이러다 보니까 디터미니스틱하게 문제를 해결하는 방법, 그 다음에 확률론적으로 문제를 해결하는 방법, 이 두 가지를 적절하게 믹스를 해야 됩니다. 우리가 모든 문제를 해결하기 위해서. 그럼에도 불구하고 우리는 디터미니스틱하게 문제를 해결하는 걸 항상 원해요. 왜 그러냐면 그렇게 교육을 받았기 때문입니다. 이유는. 그걸 수학이나 공학에서 뭐라 그러냐면 디터미니스틱하게 문제 풀 수 있는 거. 대부분 그런 문제들을 스테디 스테이트 문제다 이렇게 얘기합니다. 똑같은 말이에요. 우리가. 그러면 스테디 스테이트 상태로 문제를 풀었다라는 얘기는 확률론적 관점에서 뭐가 되느냐 그러면 어떻게 얘기해야 되느냐 저렇게 푼 거를 확률론적에서 얘기하면 겨우 평균값 계산하는 거다 이렇게 생각하시면 돼요. 겨우 평균값. 여기서 디터미니스틱하게 스페어 개수를 3개를 계산했어요. 실제는 어떻게 돼요? 3개가 될지 4개가 될지 2개가 될지 아니면 0가 될지 모르지만 평균적으로 몇 개다? 디터미니스틱하게 풀었더니 3개 나왔다 이런 뜻입니다. 같은 말이에요. 그러니까 에버리지. 우리 공학을 수십 년 동안 배웠습니다. 초등학교, 대학원까지. 공학에서 겨우 하고 있는 게 뭐예요? 지금 여러분들 하고 있는 게 계산하는 것들. 평균 계산하는 것이 잘 생각해 보세요. 내가 이때까지 뭘 계산했지? 평균값 계산한 거야. 잘 생각해 보세요. 그래서 우리가 항상 저렇게 답을 낼 수 있으면 좋지만 우리 인간이 개입이 되고 디터미니스틱하게 해결할 수 없는 문제들이 믹스가 되면 우리는 항상 다시 확률론적으로 문제를 풀어야 됩니다. 그래서 오퍼스 10이 뭐다? 디터미니스틱하게 아주 수학적으로 나이스하게 스페어 개수를 산출해줘요. 근데 이게 정답이 아니라고 그랬죠, 제가. 그러면 시나리오를 계속 바꿔가면서 시뮬레이션을 해볼 수밖에 없다 이런 뜻입니다. 확률론적 관점으로. 그래서 심록수가 필요한 거고요. 그래서 사실 되게 어려운 문제입니다. 제가 이렇게 비유를 해서 간단하게 설명을 했지만 그거 이해하는데 저도 수십 년이 걸렸어요. 왜 이렇게 하지? 두 번째 중요한 거. 스테디 스테이트란 말은 그 다음에 디터미니스틱이란 말은 시간 개념이 없습니다. 시간이 들어갈 수가 없어요. 왜 그러냐면 시간을 집어넣는 순간 어떻게 돼요? 상황이 계속 바뀝니다. 그래서 우리가 10년, 20년, 30년 이렇게 시간이라는 개념을 쫙 군수에다가 집어넣어 버리면 되게 문제가 복잡해져요. 문제 안 풀립니다. 그럼 어떻게 해야 되느냐? 아까 얘기했던 대로 확률론적 관점으로 시뮬레이션 할 수밖에 없다 이거지. 그래서 또 심록수가 필요한 거고. 우리 여기 다 계신 분들 공학을 전공하셨을 겁니다. 공학에서 시간 문제 해석을 했어요 여태까지? 잘 생각해보세요. 대학원까지 다 졸업하셨잖아요. 시간 문제 해석 못합니다. 제 아무리 아주 특수한 경우 빼고 일부 하긴 하지만 시간 문제를 일반화해서 푼다는 건 불가능합니다. 우리 인간들은. 그래서 공학에서 다루는 것들 99.9%보다 스테디 스테이트 문제예요. 기계공학에서 시간 문제 해결해요? 안 합니다. 할 수도 없고. 전자공학 일부 해요. 일부. 그럼 전자공학에서 하는 문제 푸는 게 전부가 뭐다? 스테디 스테이트 문제만 푸는 거야. 우리는 주관하고 배우는. 뭐 이론 순수과학도 마찬가지죠. 시간이 관련된 미분 방정식을 푼다? 누군가가? 불가능합니다. 무지하게 어려워요. 그래서 항상 시간을 빼고 우리는 문제를 해결해요. 왜? 시간에 관계없이 일정하다라는 전제 하에서 문제를 풀어야지 시간에 따라서 어떤 상황이 변해간다고 가정을 하고 문제를 만드는 순간 답이 안 나오는데요. 되게 어려운 문제예요. 시간이. 그래서 그런 문제를 해결하는 방법으로 우리가 여태까지 도입했던 게 뭐예요? 시뮬레이션 기법이잖아요. 그래서 모델링 앤 시뮬레이션 이렇게 얘기를 하는 거고, 이게 조금 더 발전하면 이제 뭐 AI가 나왔으니까 그런 것들도 해결할 수는 있겠죠. 어쨌든 시간은 안 됩니다. 못 푼다가 답이에요. 현재까지. 그 다음에 좀 이제 마커스가 얘기할 게 뭐 비용에 관련된 건데, 한 가지만 더 혹시 잘 아시겠지만 염려가 돼서, 우리가 비용 문제를 푼다는 건 돈의 문제를 푼다는 얘기고, 우리가 얘기하는 화폐의 가치는 어디에 있어요? 돈의 가치는 어디에 있어요? 우리 저 눈에 보이는 이런 실물 자산의 가치는 뭐예요? 프라이스라고 얘기하죠. 가치. 가격에 있잖아. 근데 우리가 실물 자산이 아닌 화폐 또는 돈이라고 얘기하는 것들은 가치가 어디에 있냐면 항상 이자에 있습니다. 오퍼스테에다가 이자율을 안 집어넣고 비용 계산하면 가치를 계산할까요? 못할까요? 못해요. 그러니까 아까 저 이자율에다가 제로 빵 집어넣었죠. 여기서 계산한 라이프 사이클 코스트는 의미가 있다 없다? 없다가 답이에요. 그래서 항상 이자라는 걸 집어넣고 이자를 기준으로 가치를 계산하는 겁니다. 여기서 얘기해요. 단순하게 100원이 10년 동안 계속 발생됐다 해서 1000원. 이러면 뭐라 그래, 이건? 어카운팅이라고 그러잖아. 회계라고 그러지. 하지만 돈의 가치를 따지는 이자를 고려하고 또 다른 요소도 가치를 고려하고 또 다른 요소를 고려해서 계산하면 뭐라 그래요? 그때는 어카운팅이란 말 안 합니다. 뭐라 그래요? 코스트를 분석했다 그러지, 그때는. 그래서 똑같은 말이지만 전혀 다른데 의외로 많이 물어봐요. 이자율을 안 집어넣었더니 NCC가 계산이 안 돼요. 당연히 안 되지. 우리는 뭘 하는 거야? 코스트 계산하는 거야. 어카운팅이 아닙니다. 우리가 코스트에 관련돼서 잠깐 얘기할 겁니다.
Yeah, so remember what we did? We had those 3 steps of improving the solution. We first of all we looked at what happened if we buy more spares. Then we look at what happened if we can have more local storage, and then we were looking at shorter transportation times. All 3 are methods of improving the efficiency of the systems. Okay. So now we'll continue, and now we've been working with a very, very basic model with just the minimum input data. But I want to show you more of the capabilities of the suite and more of the sort of a little bit more details of the models and the possibilities that we have covering the real world scenarios that you all are facing. So some other questions to be answered. So now the command needs to have an estimate of the support costs for the coming 5 years. Can we provide that? Well, yeah, our model allows us to forecast costs, but we need to expand it to capture more of those aspects of the model as well. There are, of course, a lot of different cost and cost elements associated with all this that we are talking about. Everything from spare parts that we have looked at so far, but of course, tools and equipment for performing maintenance, labor costs associated with tasks, consumables. We're talking about grease and liquids and stuff that we need to perform the maintenance, nuts and bolts and stuff like that. Yep, we've been talking about corrective maintenance. There are transportation and costs for that, and of course also preventive maintenance, which we haven't looked at so far. But 3 main contributors of support cost is, of course, the resources, consumables, and PM. So if you look at the resources and consumables, so resources can be of different types. Typically, it's either like man hours. Someone's working in the workshop, and that it costs money to have people working on stuff. It can also be the tools that you need or the actual facility itself. In a way, it will still drive costs. On the other hand, we have the tasks, and of course we need to that we're going to perform, and then we need to sum this together. This is the name of the input table in OPUS Suite, task resource. So for a certain maintenance task, we need some certain resources. Same thing for consumables. As I said, it can be all the kind of things that you need for performing the maintenance, but which is not really spare parts, or things that you don't want to include in your spare parts optimization. Stuff that is not as expensive typically. So you don't want to compare a helicopter engine for millions of dollars with some nuts and bolts or screws that just cost a few bucks each. Same thing, maybe lubricants and stuff like that. And again, same thing, when performing a task, we might need some consumables. We model this in a table called task consumable, where we connect those two elements of task. Okay, and just to remember that, so if we have poor technical availability properties, and we want to reach some kind of operational objectives, we must compensate by increasing the support system resources. And all this costs money, so that's why we coming back to this and the different areas. So then what affects the life support cost? So life support cost is the standard or the default on the x-axis of the cost effectiveness curve. That is the life support cost in OPUS 10. So we have costs for the maintenance requirements, both for corrective and preventive, but also for resources. When it comes to the support strategy, the cost can depend on whether we are doing the maintenance in-house or if it's contracted, whether it's centralized or distributed, and so on. When it comes to the maintenance resources required to perform the maintenance, there are different properties such as price, but it can also be availability or lead times. I mean, a resource, if it's a human being, it cannot work 24/7, so we might have to schedule the usage of the resources. Might also be different costs depending on the skill level, if it's a sort of basic knowledge or if we need a full engineering level. And of course, the fleet size, the number of systems, etc., will drive cost differently, the deployment locations, the number of operating hours. So all this together will fall for the life support cost. And with this, we can just kind of easily understand that we can't just say what the cost is going to be. We have to analyze, we have to calculate, to summarize all this and how it all plays together. There are two different approaches often that we talk about when we talk about cost analysis. Either we do top-down or we do bottom-up. So a top-down approach means that we start from a top level and we assume that we can make an assumption that the corrective maintenance cost is going to be X money per flight hour or something like that, and the spare parts cost is going to be Y dollars or set dollars or something for that. So on the top level, and then we can sort of break that down and say that if we say that this is the spare part cost, say that it's 10% is for the repairables and 90% is for non-repairables and so on. So we can drill down, sort of starting from an estimate at the top and going downwards. Of course, the other way around is the bottom-up approach, where we start from parameters, meaning that we feed a model with data from the bottom. So we by using formulas and saying how do we calculate the cost, we start from a parameter at the bottom, and then using functions, we can calculate the cost. So as you see here, we can reach the same type of cost with both approaches, but with the bottom-up approach, we come from values of different parameters, using functions in order to calculate the cost. And of course, once we have those costs or the cost level, we can aggregate those costs up to the total sum. But this is much easier now because now it's just a summation of the underlying costs. So summarizing those two costs will give us this aggregate, and summarizing those four aggregates will give us the total lifecycle cost. And now, of course, which one do you think will have the better prediction? Is it the top-down or the bottom-up? Well, I know for a fact that working with these kinds of models will produce much more accurate results in the end. And of course, that's something that's the idea that we suggest on how to approach it. Okay. And yeah, just to summarize, so the top-down approach would be start from estimates or references from other projects and so on, or from experienced people. It may be pretty fast and easy, but the flexibility is low because we won't get an understanding of any cost drivers from anything. And it won't give us any additional insights. However, with the bottom-up approach, we'll have a high flexibility. We will be able to understand what is driving the cost. Are there any specific items? Are there any specific tasks or stations and so on that is pushing these costs to become higher? It's data driven in a totally different manner compared to the top-down approach, because we start from the parameter values. So meaning that if we can gather this data, we can just feed the model and update it. It's very easy to update once we have new data. Rather than when we go from top down, we can't really do that in the same manner. But of course, it's a little bit more complex model, but with the right tools at hand, you will get a lot of support as well. And this is just to show you, remember we have in the OPUS Suite, we have some different tools, but what's important is that it's all integrated and we can get out a lot of information from the optimization and simulation in terms of both costs and results. So we can actually we can put values on those parameters. Remember that in the bottom-up approach, we start from parameter and values for those parameters. We can get those values once we have our models in OPUS Suite. It's very easy to get such cost parameters that we then can push into the cost analysis tool and get good estimations and good overview of the life cycle costing. And if we look at the cost model of OPUS 10, it all starts from the life support cost, of the OPUS Suite. And that's the top level. And then that can be split up in investment costs and recurring costs. Okay? And then, of course, there's a second level here. We can break up the investment cost in investment in spares and investment in resources. And when it comes to the recurring costs, the next level of this breakdown is that we can look at a lot of different things, but consumption costs, reorder costs, storage, transportation, CM and PM. CM is an abbreviation for corrective maintenance, and PM is for preventive maintenance. And of course, the resource sustainment cost. There are also additional levels here. You can drill down a couple of more levels in this cost model to get more information. I'll show you more later on. But yeah. And we remember from before, what we did this before lunch actually, when we were talking about the events modeling and the process on how it works and the maintenance that is needed when the events occurs. And that's when we were talking about failures, but then we also have PM, so some short words on preventive maintenance. So it can be different type of activities that calls for such a scheduled maintenance. Might be stuff like pre or post mission activities. So a pre-mission activity might be to fuel up your helicopter. That's a kind of normal pre-activity, but it's still scheduled. It has to happen before each mission. And then you might have post-mission activities. So It might be some cleaning or checks or other type of things that are prescribed to do every time you end your mission. It can be other inspections and checks that you're doing according to the clock. Either it's on system maintenance, meaning that it's stuff that we are doing actually directly on the system, such as a cleaning or as a fueling or armament to put on new ammunition or whatever it might be. It can also be component maintenance, meaning that you need to take something out of it. Again, the engine is a good example on an aircraft or a helicopter. You need to take the engine out of the system and send it for overhaul every year or second year or what it might be. But it's prescribed, it's scheduled. And if we look at it from a spare part optimization perspective, we can say that this type of inspections and checks, as well as the pre- and post-mission activities, they typically do not require any spare parts. However, they might induce downtime, and they might also require resources. So from a spare part optimization perspective, maybe not super important, but still important in the model, because if you're running simulations and you are evaluating detailed operational profiles and over time, then it's going to affect the availability of the systems. And if you're doing cost analysis, it's also of interest. On-system maintenance could require spare parts or consumables, and it probably induces downtime. So here it's important also for the spare part optimization to get true values out of both cost and availability of your systems. And of course, component maintenance it requires spare parts, so it's definitely of interest for spare part optimization. It will also induce downtime, so it's again interesting to analyze for all reasons, as well as it requires resources and drives costs, etc. So what are the implications on the spare parts when we talk about preventive maintenance? Well, now we have two different sources of item demand. We have one from the failures and one from preventive maintenance. Both needs to be served by the same stock. However, they might have different turnarounds, so the time it takes until the item gets back will be different for different type of failures. So whether it's a repair or a PM or scheduled maintenance can be different, but they are still served from the same stock. So it's the same spare parts that are used to replace the demand, no matter where it comes from. And this is really one of the what should I say, strengths with OPUS 10, that we can handle this combination of both random and scheduled demands into the same model. Because, both will impact availability, of course. So, how do we input preventive maintenance in OPUS Suite? Because it's a little bit different compared to the failures, where we just have this failure rate. But here, it's more of a prescribed plan, so we need to give an interval. Just as for the failures, it can be in different operation parameters, so either operating time, calendar time, kilometers, as we mentioned before. Also, it can be, the PM is typically connected to different components, either to the entire product variant, or to specific breakdown elements, or to single items or hardwares. And then each of those activities will require some actions to be performed, which are described as maintenance activities. And if you take a simple example on a schedule for preventive maintenance. So let's say that every 500 hours, we have to do a minor overhaul. Okay, so you see here some kind of workload on the y-axis and time on the x-axis. So every 500 hours, we perform a minor overhaul. And then we have every 1,000 hours, we're doing an intermediate overhaul instead. And this is interesting. Probably, and in most cases that I've seen at least, doing such a thing includes also the minor event. that. So see it as maybe the service intervals for your car. Right? If you have a 500,000 kilometer interval or something, or 5,000 kilometer, then you're doing like a small service in the car. But then every 10,000 or 1,000 kilometer, you need to do a medium service. But then that means that they're doing this small one plus some extra stuff. So it's often included there. And then, of course, we might have some really big or large services that we do every 2,000 hours. But yeah, I think you get the point. So for the major overhaul, we typically include the smaller ones, but we do some additional stuff as well. And this can be handled very nice in OPUS Suite actually, so we can define how the maintenance schedule looks in detail. Okay, let's move into OPUS Suite and add some of these extensions, expanding the model. Okay, so we are back in OPUS 10 here, and we start from one of the files we had before, from the local stock. So moving back here, so I'll start from the one that I called the local store here, where we allowed for items to be placed at the local stores as well. So if we go from here and we want to add some additional information here to get more costs into the model, because that was the original question there, if we can have a better cost picture. And I'm just going to run a calculation on this file, so we have that. And then I'll go back to the input and I'll save this file with a new name. So we again create a new one. The first thing we're going to add is the fact that one of the items in our models is not repairable. So this means that we need to buy new ones every time they fail, which is often referred to as a reorder. So I add the name reorder to this model. Okay, and to do that, and here it's the compressor blade. So it's this item here. All right. So to do that, to reflect the fact that it's not possible to repair it, we are setting the property on the corresponding failure to show this. So here in the failure table, I actually showed you this earlier today as well. So if you remember, there is a column called repairable, which we can set to yes or no. And here we want to say for the compressor blade, it is non-repairable. So set no. And then we need to add information about what happens when this one fails, because now we're not going to repair it anymore. So first of all, I should go to the repair table, look at, and then I can, if I right click, here's a pretty good functionality actually. If I right click, there is something called deactivate rows. If I click that one, you see how that row turned red here, meaning that it is, it's not active. So we're just going to ignore it, or the tool is going to ignore this row when we're reading the input. And it's a good way, I think, when I'm testing stuff and so on, and in the model, it's kind of nice to just deactivate the row. Of course, I can activate it again. It's just right-click it, and there it is, activate rows, and it's back in again. So again, deactivate. All right. Anyway, we needed to define. So since we are not repairing it, we need to define what we will do with it instead. And note how it turned blue here in the tree, the structure tree as well, turned blue there. So I need to insert another table, and it's called reorder capability, with describing how we can reorder this one. So it is the compressor blade here. So I select as item identifier. Select the compressor blade. And so from what station can we perform this reorder? I'll have a quick look in my Excel spreadsheet here. We do that from the central station. So the reorder is performed at the central station. So we select central here. And the lead time, which means the time it takes until we get a new one, is 730 hours. So actually the same time that we had as a repair time for the items. But this means that when we order a new one, it takes 700, which is 1 month. So it takes 1 month, and then we get a new compressor blade to the central, and then we can distribute it out to the bases as well. But there's also ordering the cost for setting up these reorders. So here it costs $1,000 or whatever currency we're working with. So there's a ordering setup cost of 1,000. So every time we do this, it costs an additional 1,000 money. But of course, we also pay the price for one of those items every time. So that's what we need to do to run the calculation here. So just calculate. And what happened? Well, the curve looks kind of similar, but it jumped a long way to the right, as you see. So this is the orange one, is the one with the reorder. And if we compare let's compare some costs here. I showed you before, and also how we can look at the results, for example, through this table, but it's also possible to look at reports. There are more static reports available, and there are a lot of settings to do around this. You can select a lot of different tables, but anyway, pressing that just to show you, pressing the report button here, we get the default setup for the report tables. And you see on the left here, we also get a node here for report in the Explorer view. And then I can open it up, and here's the default sets of result tables, or report tables. And there's one called LSC summary. Look at that one, and we see here that how the costs are distributed. You might recognize here the breakdown. We see the different levels. So top level is life support cost, 467,000, and then that's divided into the two elements on the first level, which is the investment cost, 107,000, and recurring costs, 359,000. And this is for point number 42. But it can be that we want to compare this now to the other curve. So just going to make sure that I can run a report on this one as well. So select the corresponding point on the original curve, so sort of same availability, but and running the report there. Gives us another report, and it is, of course, it's down here, LSC summary, and we can arrange the windows a little bit so we can see them at the same time. Here we go. So trying to put them next to each other so we see the difference. They are fairly similar in terms of investment, a little bit lower here. I don't know if I got the exact right points there, but they are, as I said, they are similar, around 100,000. But for the original one, the one without the reorder, you see that the recurring cost here is 0. Right? So there are no recurring costs, we only have investment costs. However, for the new scenario here with a reorder, we get a lot of recurring costs, 359,000. So, and that's due to both the consumption cost of items, because what happens now is that if you remember, we set something called the scenario length to 5 years. We did that earlier. So with that said, OPUS will calculate how many reorders we are doing on average per year, and then it will multiply that with a number of years according to the scenario length. So, and it's not only the consumption cost, because we said that it also cost an additional 1,000 each time we perform the reorder. So we have a pretty high reordering cost and consumption cost there, which makes the total life support cost become much higher compared to the original case. That's also why the entire curve has moved far away to the right with a much higher cost. We can also look at we look at some more results here in the result table, looking at the items. I'm going to show you here some what's available. We can look at, for example, the typical results for non-repairable items. Okay, so we want to see the reorder size. Reorder. And of course, we are only interested in the compressor blade here. So I thought, okay. I think my computer is getting tired. But, so I'm looking at the compressor blade, and as you see, those values are only available for the central, but my screen is a little bit not so wide. But so here are some interesting figures that we can get out. For example, it says that the time between reorder, TBREO, time between reorder, is 3,464 hours, calendar hours. So that means that probably we'd have somewhere around and then we can also add another one, items consumed per year, also an interesting parameter in this case. So you see that every year we are consuming on average 38 items of this compressor blade. We have a quantity, we have 13 systems in total, etc. But the time between reorders looks like this on average then. And then the reorder size is something that OPUS calculates, which corresponds also to the reorder point. I should actually add the stock size too. I'm just coming up with a lot of additional ones. But this is just to show you how it calculates those things. At home, or when I work at my office, I have a much wider screen and it's easier. This laptop screen is a little not so wide. So what happens here is that OPUS then calculates an optimal spares package here, saying that we should have 18 of this item at the central store. And so when we reach the reorder point, meaning that this 18 items that we will take from them until we get down to 3. And when we have only 3 left, we order 15 new ones. So these are also results that OPUS produces. It helps you not only to optimize the actual stock size, but also the other measurements such as reorder point and reorder size here. Yeah. I also want to show you this very same file in the world of simulation to show you some more analysis that can be done there. So I take it here. I forgot to do this. We should do. Let's select a point here because when we want to run the simulation, we need to select which point of spare parts we want to analyze. So what I do is I select this point with the first one with 95% availability, and I say that I want to insert this allocation into this very same case. So click OK there, and then if you remember the table called stock allocation. We should probably be able to see it here. It was point number 16, and we see the values of the stock size and reorder size